Oh, okay, his slides are up. Matthew, knock them dead.
Okay. So today I'm going to tell you about some work we did in the direction of performing a root cause analysis of BGP routing dynamics. And the basic idea of what we're trying to do is we passively observe routing updates at multiple vantage points. And from these updates, we try to infer information about the types of events that are occurring. In particular, we try to infer information about the location where and the reason why these events are taking place. So to motivate this problem, we note that it's widely believed that inter-domain routing suffers from a wide variety of problems, including persistent instability, slow convergence after changes, and misconfigurations. The key difficulty with developing techniques to address these problems lies in the fact that we have poor visibility into the dynamics of BGP. That is, we can observe a large number of updates being received at an individual BGP router, but we don't, in general, have a clear picture of why these updates are being generated and where they're coming from. In particular, we'd like to be able to answer questions such as, what are the spectrum of possible causes of route changes? What are the primary causes of instability? And how does BGP respond to a routing change? And again, the key difficulty with developing good techniques to address these problems is that if we have an incomplete model of BGP and an incomplete model of the workloads it's under, we're going to develop incomplete solutions to these problems. So the approach that thank you. Is this better? Thanks. So the approach that we're arguing for involves the design of a BGP health monitoring system. We envision that autonomous systems will volunteer to peer with the health monitor. The health monitor can then collect routing updates from these different vantage points, perform inference over them, and then distribute the inferences back out to whoever's interested in receiving them. The key advantage to using multiple views lies in the fact that we can achieve greater visibility into the events occurring in BGP. So my focus in this talk is not going to be on the complete design of the health monitor. Rather, I'm going to focus on one core aspect, which is how to do the inference. So we envision that there are several possible uses for a health monitor. First, we think it might be useful for network operators as a tool to assist in troubleshooting and diagnosis of various events. In addition, perhaps BGP policies could be set based on historical statistics of link and node stability. Perhaps this information could be used in an online manner to assist in path selection. And in addition, perhaps customers could use this information when deciding which upstream providers to use and to peer with. So first, before I define the problem, let me first define some terminology. I'm going to define an event to be some activity taking place at some location that generates one or more routing updates. I'm going to define a suspect location set to be a set of possible locations where the event could have occurred. And similarly, I'm going to define a suspect cause set to be a set of possible reasons why the event took place. Then the problem that we're trying to address is, given a set of routing updates observed at multiple vantage points, determine the suspect set, which consists of the suspect cause and suspect location sets, of routing events that trigger each one of these updates. So when we started performing this study, we did some analysis, and we found that the update rate at a BGP router could be classified into one of two categories: quiescent and turbulent periods. During quiescent periods, we would receive fairly small numbers of updates affecting small numbers of prefixes, and these tended to last for long periods of time. But occasionally, we would notice these very massive spikes where we would receive a large number of updates affecting a large number of prefixes in a short period of time. The first stage of our algorithm involves separating between these two periods of time because the types of events that are taking place, and hence the types of assumptions you can make, are fundamentally different. During quiescent periods, it's likely that a number of independent events are occurring. And hence, during these periods, we make the relatively safe assumption that bursts of updates to individual prefixes are correlated, that is, are caused by the same event. During turbulent periods, it's highly unlikely that a large number of independent events simultaneously happen to occur. So hence, during turbulent periods, we assume that one or a small number of very major events took place that caused the majority of these updates. And this is a more powerful assumption, and it allows us to do more precise inference as we have a larger amount of data, a larger number of updates to work with. The reason why we don't make this assumption during quiescent periods is because it's much more likely that independent events are occurring. And if we assume that two correlated observations are independent, we'll harm precision, but we will not harm correctness of our inferences. Whereas if we assume that two independent observations are correlated, and do inference over both, then we can harm correctness, and that's particularly undesirable. So again, the first stage of our algorithm involves separating between quiescent and turbulent periods. During quiescent periods, we did some analysis, and we found the update rate to a prefix could be characterized as long silence periods where there would be no updates, followed by bursts of activity, followed by more long silence periods. So during this phase of our algorithm, we search for these bursts, and we assume that each update in the burst is correlated, that it is caused by the same event. And then we define a set of rules that map from the contents of the burst onto the suspect set. So when performing this analysis, we found that there's a number of prefixes that are continually updated over long periods of time and that never converge. And we define a separate inference algorithm for dealing with these that I'm not going to go into detail today. So we run this algorithm in isolation at each of the viewpoints, and then we search for bursts of updates that happen at nearly the same point in time to the same prefix across several views. So you can imagine that if a route or a prefix gets updated at nearly the same point in time at more than one view, those updates are likely to be correlated. And so this allows us to refine our inferences across multiple views. During turbulent periods, again, we make the assumption that most of the updates we received are caused by the same event. So here what we do is we search for commonalities across these updates. In particular, we search for autonomous systems that occur in a large fraction of the AS paths that we observe. And these ASs are suspect for having caused the event. And we define a set of rules for doing this more formally, and then we output the suspect set. So next, I'm going to go through several examples of our inference rules. And for the purpose of these examples, I want you to assume two things. First, assume that community attribute changes don't occur, and assume that autonomous systems are singly peered. We don't make these assumptions in our algorithm, but they make the examples easier to follow. So this is the first scenario. Suppose we have this AS level topology with a viewpoint at V at which we're observing routing updates. And suppose C contains 1,000, D contains 3,000, and E contains 2,000 prefixes. So in this scenario, suppose we observe 1,000 prefixes updated within a short period of time that use the link AC. In this case, we would say that link AC is suspect for having undergone the event. Next scenario, suppose we observe 4,000 prefixes updated that use link AB, and of these, roughly 2,000 use BD and 2,000 use BE. In this case, we would say that AB is suspect for having undergone the event. BE is not suspect because an event taking place on BE wouldn't have affected the other 2,000 prefixes that traversed AB. Next, suppose, on the other hand, we observe 2,000 prefixes updated that use AB, and of these, roughly all of them use BE. In this case, we would say that BE is suspect. Again, AB is not suspect because an event taking place on AB would have likely affected the other 3,000 prefixes that traversed AB. So I'm oversimplifying things somewhat. There's a number of issues that we had to address to develop a more correct solution. First, the effects of simultaneously occurring independent events can be overshadowed by major events. That is, if a very major event takes place that affects a large number of prefixes, we might not be able to detect more minor events. However, sometimes we can use multiple views to detect these independent events. Next, occasionally, two large events may simultaneously occur. And this is a problem because the rules that I just defined only assume that only a single event occurs at a time. So we had to develop some additional techniques to separate out the effects of these different events from each other and perform inference over each in isolation. Finally, we need to be careful about when we transition between turbulent and quiescent periods. We solved this problem by the use of thresholding, but the question remains, where do we place the threshold? How many prefixes need to be updated to signal the start of a turbulent event? So we did some analysis, and we found that the update rate to a BGP router was multimodal, and therefore it makes sense to place the threshold between these two modes. So here's an example of how we do inference during quiescent periods of time. Suppose we have a viewpoint in S, and we're observing routing updates to a single prefix contained in D. Suppose over a long period of time our path is previous path, and then there's a flurry of activity and our path reconverges to be final path. So there's a number of events that could have caused this change to occur. For example, maybe a link failed in the blue region, or maybe an AS in the yellow region advertised a lower MED. However, there's a number of events that could not have caused this change to occur. For example, a link failure in the yellow region, or an AS in the blue region advertising a lower MED. So in general, we can say that either some event took place in the blue region that worsened the properties of the path, according to the BGP path selection process, or some event took place in the yellow region that improved the properties of the path. So this set of inference rules works in this fashion. We define a set of equivalence classes that contain events that produce similar observations at views. For example, improved and worsened are two equivalence classes. We then define a set of rules that map from the contents of the burst of updates onto these equivalence classes. And then we can use these equivalence classes to narrow down on the set of possible causes and set of possible locations. So here's some additional rules for how we can perform inference across views. Suppose we have two views, view 1 and view 2, and they're observing bursts of updates to a prefix contained in autonomous system D. Suppose in the upper case, view 1 and view 2 both observe a burst of updates affecting that prefix. Then it's likely that that event did not occur in the yellow region. If it had, for example, if it had occurred between V1 and A, then only V1 would have observed the event, and V2 would have not observed the event. Similarly, assume that view 1 observes the event and view 2 does not observe the event, as in the lower diagram. And suppose furthermore that view 2 has an advertised path to the prefix that remains advertised throughout the event. In this case, we know that flap damping has not been activated at view 2, and hence we can say that the event did not occur in the green region. So again, I'm oversimplifying things somewhat. There's a number of issues we had to address. So again, simultaneous events can occur. And again, the rules I just defined assume that only a single event occurs at a time. So we did some analysis and we found that simultaneous events during quiescent periods are rare. Furthermore, we can sometimes detect simultaneous events. For example, if you observe a flap in one view and a reroute in another, or if you observe an advertisement in one view and at the same time a withdrawal of the same prefix in another view. To our knowledge, there's no single event that could have taken place that could have caused both these observations to be made. So in practice, when running our algorithm and we detect that simultaneous events occurred, we turn off all rules that assume that only a single event occurred. Next, I had asked you to assume that community attribute changes don't occur. These changes are unique in the sense that they can cause a routing change to take place several hops away from the AS that changes the attribute. So what we had to do is we had to modify our rules to include every AS that could have changed a community attribute. Finally, I had asked you to assume that ASs are singly peered, which is not a realistic assumption. Let me show you why the issue of multiple peering links can complicate inference. Suppose we have these two network level topologies, which are identical from the AS level. In the case A, if AS1 observes an update to a prefix contained in AS5, but AS2 does not, we would know that the event took place between AS1 and AS3. However, in case B, we can no longer make such a claim because the event could have also occurred between AS3 and AS4, or AS4 and AS5. So again, we had to modify our inference rules to take this into account. So validation was a very tricky problem for us because ISPs are understandably unable to provide us with the sorts of events that we need to use to validate our study due to the sensitive nature. However, we came up with a list of 3 ways to validate our approach. Although we were unable to precisely validate each one of our inferences, we were able to validate a certain set of core rules that we used in our algorithm. So first, there are a number of well-known historical events that took place that we can use to validate. For example, on October 3rd, 2002, UUNet underwent a major routing anomaly that broke a lot of routes traversing UUNet. So we came up with a list of 6 such major events, and we verified that our approach was able to pinpoint the cause in each of these 6 events. Next, we looked at periods of time when internet worms were propagating, and we detected increased numbers of session resets during these periods. And this makes sense because some people believe that internet worms cause increased levels of congestion, which can contribute to BGP session resets. Then we use BGP beacons to validate. BGP beacons are well-known prefixes that are advertised and withdrawn according to a well-known schedule. We verified that our approach was able to correctly detect each of the beacon events that we observed during a 1.5-year period. Finally, we used the observation that if a view inside of an AS observes an update to a prefix contained in that same autonomous system, then we know the event arose inside of that AS. And we use that observation by making inferences at other views and checking for conflicts with the inferences made at that view. And we didn't find any conflicts during the 1.5 years over which we carried out that study. So now I'm going to show you some results. First, we came up with a taxonomy of different types of events that could occur in BGP, and we found the number of updates attributable to each cause. In particular, you'll notice that 45% of events are caused by turbulent events, where a large number of prefixes are updated. So in terms of location, we found that 70% of updates using our technique could be pinpointed to a single inter-AS link. And we can achieve more precise inference for more major events. So if there's a very major event that affects a large number of prefixes, we'll receive a large number of updates, and we can typically infer more precisely. In addition, we found that a small number of autonomous systems and a small number of links appear to be causing the majority of updates that we observe. And we came up with a list of several previously unknown major events, and these are detailed in a website I'll mention in a bit. So for future work, we're interested in further investigating this class of continuously flapping prefixes that are continuously updated over long periods of time. We're curious whether statistical inference techniques could be used to improve precision of our inferences. We'd like to develop a set of guidelines for placement of views. So to answer questions such as where to best place a view to maximize visibility into a set of links or a certain type of event. We're currently working towards developing a set of alarms and triggers to distinguish healthy behavior from unhealthy behavior. And along these lines, we've developed an analysis that's running in real time on this website. And the purpose of this analysis is to hopefully get some industry feedback about the correctness of our results. So if you work for an ISP, or if you know somebody who works for an ISP that has any sort of data that could be used to validate the results that are on this page, we'd really appreciate hearing from you. And I guess I can take questions now.
30 seconds, or as long as it takes for Christopher to get up. Any questions? No questions now? Get him at the break. Thank you very much.
Thanks.